All right. So in the last few classes, we are deriving the current equation of PN junction, and we derived the current equation for wide base diode case and narrow base diode case. And so these are the two equations that we have derived. For a wide base, right? So for for a wide base, your current will be in this form, right? So this is q n I square dn by nln plus dp by ndlp into e to the power q applied voltage by kt minus 1, right? So and for a narrow base diode, for a narrow base, so narrow base is when the wp and wn are less than lp and ln, right? So in that case, your total current will be so your ln lp will be replaced by wp and wn. So the current will depend on applied voltage, as well as current will exponentially depend on applied voltage, as well as it will also depend on wp and wn. By varying in narrow base case, by varying the wp and wn, you could also vary the current. All right. So this is the overall equation. So today we'll mostly focus on the reverse bias. So in the reverse bias case, um, so in the reverse bias, so basically your in the reverse bias, if I talk about reverse bias, right, uh, your e to the power q via by kt will be less than 1, right? So will be will be less than 1, right? So in that case, so if you think about wide base case, then your current will be q n I square dn by nln plus dp by ndlp, right? So okay, and so basically so basically e to the q vr by kt will neglect, so this current will be negative, uh, right? So this is my total current, and for a wide base case, I could also write it like that, right? Q n I square dn by na times WLP dp by nd times Wn. So this is we call it the reverse saturation current. Um, right? Okay. So here you see, if I plot this currents here, right? So I'm mostly talking about reverse bias. So let me concentrate on the reverse bias case. Um, so your applied voltage is, let's say, negative, right? If you're applying this voltage to P, um, right? So this is your applied voltage, right? So this is your forward biased case, and this side is your reverse bias. Your applied voltage is negative, and also your current is negative. The current direction changes, right? So here we saw that this current, that is all those factors that are talking about, right? So dn, na, ln, dp, nd, lp, ni. So they are all constants, right? So once you fabricate the diode, so these parameters are all constants. So your current is constant, right? So basically, you see, your current will be constant. So somewhere like this, right? So your current is constant, right? And this current, so this is your reverse saturation current. But these currents will depend on ni, so your intrinsic carrier concentration, and also the doping of p side and n side, right? So if you have lower ni or higher ni, so your current will change accordingly. For in case of germanium, your ni, your intrinsic carrier concentration is higher, so your reverse saturation current will be higher compared to gallium arsenide, where your ni is much lower. Okay, so this is a ideal case, but as you go on increasing the reverse bias, at some point of time, your current will increase. So we call it breakdown. So we'll discuss in detail the breakdown points. Sorry, the breakdown voltage. So this is called the breakdown voltage of the diode, right? So But before breakdown, basically what happens is in this region, right, we are assuming that current is constant, right? But if you look at your PN junction, let me copy it. Let me take to the next page, right? So so we know that if I draw the field, right, so field is increasing. So if you see your field is increasing and it is maximum at the edge of the junction, at the PN junction, then again it decreases, and here the field is maximum, right? So basically if you plot the field, so this is uh, so uh, this is Ex. So E at minus xp equal to 0 equal to E at xn, electric field at xn. And but at 0 point, so electric field is maximum, right? And this maximum field, we know this is nothing but q nd xn divided by epsilon, or q na xp divided by epsilon, right? So this thing we have derived, right? Please keep in mind, right? So derivation that we have done for a for a constant doping profile, right? So when you talk about doping profile in the P side, so I am talking about a doping profile which is abrupt, right? So this is Na and this is Nd, right? Um, so this is X, and this is my X, this is my Nx, right? So this is the abrupt doping profile I'm talking about, because these derivations I have done for these kind of doping profiles. But if the doping profile are different, right? So if I have a linearly graded doping profile, then your equations will also be different, right? And you should learn how to derive those equations. All right. So this is my maximum field for this case is q ndxn by epsilon, or q na xp times epsilon. And right, so we know what is the value of xn. So if I remember, I don't remember, so the xn is 2 epsilon vbi plus applied voltage na q nd by na plus nd, right? So this is my xn, and my xp is also 2 epsilon VBI plus VR. Applied voltage is added because you are operating the reverse bias. So so basically, if you take this x and x value, put, and you could calculate the your maximum electric field, which is at the junction. So the maximum electric field will be in this form, right? Let me write down. So this will be 2 times q, means you could VBI plus VR divided by epsilon Na Nd by Na plus Nd, right? Okay, so this is my maximum electric field, right? And you see, as you go on increasing the applied voltage, the reverse bias, right? As you go on increasing the reverse bias, your field is also changing, right? So the field, so basically the field is in this region only, depletion region, right? Other part is neutral. So the field is also changing. So when the field is changing, so you have also some generation process, right? We will discuss about this generation process. That means electron hole pairs are generated. So because of this electron hole pair generation, there will be some extra additional current, right? So basically, when I'm talking about this current here, right, J0, right? So towards the end of last class, I discussed, right? So this J0 is nothing but uh, electrons moving. This J0 is because of electrons moving from P to N, right? and holes moving from N to P, because electron is a minority carrier in the P side, hole is the minority carrier in the N side, and this reverse bias, reverse saturation current is because of minority carrier drifting through the depletion region, right? So but since I also, when they're drifting through the depletion region, so there is a possibility of generation, right? So we'll discuss about this generation process. So that due to generation, we have some extra electron hole pairs generated, and so this current that we are talking about, this is actually, if you look at the practical diode case, right? So there is a slow rise. So this current is not constant. So there is a rise, right, like this, right? So there will be rise, then it will break down, right? So this rise, slow rise, is because of generation. So this is because of the generation process inside the depletion region, right? Inside the depletion region, right? So when I talk about this generation process, so we have uh, so we have two kind of generation process we'll talk about. So one is actually generation. So one is, we call it avalanche, right? Avalanche generation. So this is avalanche generation. And another case, we'll also talk about tunneling, because tunneling also happens during this reverse bias condition, right? So we'll discuss about these two things. And tunneling is mostly, we call it Zener tunneling, but this is a typical tunneling uh, which is happening, right? Okay, so this is my electric field, or maximum electric field, right? So um, so what happens, right? So this maximum electric field, this is the electric field at the junction, right? So this is the electric field at the junction, right? At junction, right? So as you go on increasing your applied voltage, right, your maximum electric field at the junction, the field at the junction is also increasing, right? So but the silicon could withstand a certain electric field, right? And that field we call the critical field, and this is for every material, the critical field is different. So this critical field, so if your em is, a maximum electric field is greater than critical electric field, actually your junction will break down, right? So your junction will break, right? So basically, you have a lot of avalanche multiplication. We'll see junction will break, and this critical electric field is a function of your band gap and any other thing, right? I'll not discuss about those things. So your critical field, electric field, is material dependent parameter, right? So for silicon, uh, you have a particular critical electric field. For germanium, your critical electric field is different. So this is a metal dependent parameter, right? Right. So so if you see, if I copy this equation, um, right? Um, right. So at critical electric field, so basically E critical. So basically at, so that point VBI plus applied voltage is your breakdown voltage, um, divided by epsilon NAND by Na plus Nd, right? So so here I see when, I mean, because as you go on increasing applied voltage, at some point your maximum electric field at junction will hit critical electric field. At that point it will break, right? At that junction voltage, that applied voltage is called the breakdown voltage. So you know that VBI plus VBR, because your breakdown voltage is much higher than um, VBI, right? Because you see your VBI, um, you will be around, it will be around 1 volt, right? Your breakdown volt, I means your inbuilt potential, that will be around 1 volt, but breakdown voltage is much higher than 1 volt, right? So so your critical field, you could write also 2q breakdown voltage divided by epsilon NAND divided by Na plus Nd to the power half. So from here you could write down um, so E critical square epsilon divided by 2q, right? Na plus, so I could write down 1 by Na plus 1 by Na, right? So this is the equation of your breakdown voltage. So you will see that breakdown voltage will depend on critical electric, uh, it will depend on critical electric field, right? Critical electric field. So critical electric field also depends on the band gap, right? So higher the band gap, higher is the critical electric field. So it will depend on critical electric field, and it will depend on doping, Na and Nd, because other parameters are constant. Epsilon is constant and Q is constant, right? So for a right, um, so for a n plus p diode, right? N plus p diode. So your critical electric field you could write down as, right. So this will be 1 by Na, right? For n plus p diode where Nd is much higher than Na, so your critical electric field you could write down sorry, your breakdown voltage will depend only on Na, right? So your critical field will, I mean, your breakdown voltage will depend on Na. Similarly, for a P plus N diode, your breakdown voltage, so right. So for a P plus N diode, your breakdown voltage will depend on Nd, right? So this is for N plus P diode because as I told you, the N plus P diode and P plus, so most of the devices either have N plus P junction or P plus N junctions. And for a N plus P junction, your breakdown voltage will depend on the P type doping or doping in the P side. Similarly, for a P plus N junction, your breakdown voltage will depend on the doping on the N side, right? Okay, so basically the breakdown voltage is inversely depends on Na and Nd. So if you want to have a junction with very high breakdown voltage, then because your critical electric field for silicon is constant, right? So you just have to play with your doping profile, right? By changing the doping profile, you could change your breakdown voltage. Okay, so this is about breakdown voltage. So what are different breakdown processes, right? So so let's see how this breakdown happens, right? And how, means I was talking about generation. How does this generation process uh, happen in the depletion region? Okay, so before that, anybody has any questions here? Okay, let's say I have reverse bias junction. So I have a reverse bias junction. This is my applied voltage here. So if I want to draw the band diagram, so how does the band diagram look like? So let me draw it. So I cannot draw the formulable, but anyway, so because I have already applied reverse bias, so so this is my EFP. Let me draw, and this is my EFN, right? This is EC, EV, EFP, and this is EC, EV in the inside. So let's write down there CP, EVP, and this is my EFN, right? And I know that this difference between EFN and EFP is your uh, Q times applied voltage, right? So here you see your applied voltage is negative, so I am pulling the EFN down, right? So your energy is minus Q times VR, so the formula will be pulled down by Q times VR, right? So there is a difference. Okay, so here you see, so let's assume, um I mean, I'll assume that, assuming let's assume that this is a P and N plus junction, right? So let's assume that this is, we have a P and N plus junction. So what do you mean by P and N plus junction? So as I told that in the reverse bias, the current is because of drifting of minority carriers. So we'll have minority carriers. So minority carriers in this side will be Ni square by Nd, and this side I have a minority carriers of Ni square by Na. Since I am applied, I mean, I have assumed a P plus N junction. That means Na is lower than Nd, because I have a N plus junction, Nd is very high. So the minority carriers in this side will be very less. So I could neglect those minority carriers, right? So what are the minority carriers in the P side? So I have holes, right? So holes here and electrons. So I am assuming that a number of minority carrier holes is very less, right? So let's say I have means let's say this is a PN plus junction, and if my ND is around 10 to a 20, that means I have only one hole, right? If ND is 10 to a 20 in the equilibrium condition, I have only one hole, right? So if Ni is 10 to a 10, right? But if this is 10 to a 17, that means I have if Na is 10 to 17, then I have 10 to 3 electrons, right? Assuming Na of 10 to 17, right? So, so the reverse current, because your holes will flow from N to P and electrons will go from P to N, but since the number of holes is very less, so the total current is because of electron current, right? So this is the assumption, right? Okay, so for a P plus N junction, so now I have an electron here, right? And I have the what is the direction of field? The field is always N to P, and I know that this field is a function of applied voltage, right? So the field will increase. This means electric field is a function of applied voltage, is a function of applied voltage, and if I increase the applied voltage, your field will increase, right? Okay, so so now I have a field, so electrons, uh, let's say this is my depletion region, right? So that electron is accelerated because this, so the electron is moving because electron will go from P to N, and you see, if you look at the band diagram, there is a slope, right? So which actually this slope doesn't, this slope just tells you the electric field, right? So this force on this electron is Q times electric field, right? Minus Q times electric field. So the electrons will move with very high force, because higher the electric field, electron is moving, right? So basically what happens is the these electrons have very high kinetic energy, and this kinetic energy depends on the applied voltage, right? If I have higher reverse bias, then I have the electron has very high kinetic energy, right? So the kinetic energy is nothing but the difference between this ECN and ECP, right? So if my difference between ECN and ECP is higher, these electrons have very high kinetic energy, right? So when they're accelerating from P side to N side, so they really have very high energy. So what happens? They undergo collision process, right? Collision means they interact with the lattice, right? Basically, here I'm assuming that. So let's say in this depletion region, I have lattice, right? So because I have this acceptor and donor ions, right? When the electrons are moving from P to N, they interact with this lattice atom. So when they interact with lattice atom, they also give some of their energy, right? So let's say electron has this um, kinetic energy. So here, so they could lose energy, and this much energy they could give to the lattice, right? So what do you mean by lattice? So lattice means then in the lattice we have basically this lattice could take this energy, and it could uh, inject one electron from valence band to conduction band, right? So right, so so now I have one electron. So and then here in this case I still have this electron which has lost some energy, but I have another electron coming from the valence band, right? And similarly I have a hole here, right? I have one hole, now I have two electrons, right? Okay, so now these electrons will also accelerate, these two electrons will accelerate because this in the field, again they will also lose, right? So when they lose, then they excite two electrons, right? So basically I'll have E plus E, now I'll have two more electrons because these two electrons give energy to interact with the lattice, also they transfer their energy to the lattice, and two more electrons are coming from valence band to conduction band, right? In that process I have two more electrons, so now I had four electrons, two holes, right? Sorry, I have one hole, then I have another, so right? So in this way, so this is called the multiplication, and this is called the avalanche multiplication, because in this way what will happen when the electrons are going through this going through the depletion region, so they are creating more number of electron hole pairs, and this is the generation process that I was talking about, and this is called avalanche multiplication because they're multiplying, right? So 1 to 2 to 4 to 8 to 16, so this is how they will multiply, right? At some point, right? So and this process depends on the electric field, right? Because the electrons gain energy from the electric field, right? Right. So they have to. So basically, if they are very high energy, they could give some of their energy to the lattice, and one electron will jump from valence band to conduction band, right? But they should have that much energy, right? So that's the reason this process totally depends on the electric field, right? So as you go on increasing the electric field, so the avalanche multiplication will increase because they have very high energy and they could excite electrons from the valence band to conduction band, right? Excite means this is an interaction process, right? So electrons give energy to the lattice, and now the lattice has some extra energy, which so that the electron from valence band go to the conduction band. Okay, so this is called avalanche multiplication, right? So if you see here, so I have injected only one electron, and I'm getting more than one electron, right? So if I see about this current here, let's say the electron current at xp uh, was I0, right? Let's say I0, right? And electron current at xn, because more number of electrons are coming out, so let's say this is some factor into I0, right? And this is called, this m is nothing but you call this multiplied factor, and this is the impact transition, right? Impact transition coefficient we many times tell, right? So and this m, um, okay, so so this m is the multiply. Okay, so this m is the impact transition coefficient, or the multiplying factor, right? So if, right, so when so basically, so your breakdown will happen when the breakdown will happen when this m tends to infinite, right? Breakdown will happen when this m tends to infinite, right? So when n becomes very high, right, very large, right, so your breakdown will happen, right? And that voltage is a breakdown voltage, right? It means at that, I mean, at some point your m is so high that your current is very large, right? Your reverse saturation, reverse current is very large, and your junction will break. I mean, junction will be destroyed, right? And that is called the breakdown voltage. And again, so this breakdown voltage depends on different things, right? So means imagine, so the electron is giving energy to the lattice, transferring some of its energy to lattice, and lattice is enabling one electron to come from the valence band to conduction band, right? But if your band gap is high, then let's say I'm talking about gallium nitride, which band gap is 3.4 electron volt, right? then you need more energy, right, to create this electron hole pair, right? That means the breakdown voltage for a high band gap semiconductor, let's say gallium nitride, is much higher than your breakdown voltage of silicon. So that is called the critical field, right? So that's why the critical field, the critical electric field of gallium nitride is much higher than silicon. Similarly, the critical electric field of germanium will be much lower than silicon, because germanium has a lower band gap. So it's very easy to excite electrons to generate electron hole pairs, right? Right. So uh, so that's the reason the lower band gap materials have low breakdown voltage, right? So if you have similar, let's say you have N plus P junction, P plus N junction in this case, made of germanium or silicon or gallium nitride, you will see that for germanium case, your breakdown voltage will be lower. Silicon case, it will be somewhere in between gallium nitride and germanium. Okay, so any questions here?
So here I naught is the reverse saturation current.
Yeah, so this is, if there is no multiplication, so your I naught will also come out, right? Means I naught, yeah, reverse saturation current basically. So what I'm talking here is, so let's say there is no multiplication. So the current at this point will be current at this point, because nothing is happening inside the depletion region, right? And that will be your reverse saturation current, right? So in this case here, if I, yeah, in this point here, right? In this point here, right? But as I told you, right, so as you go on increasing your reverse bias, there is electric field is little bit increasing. So there is possibility of, so there is a possibility of generation. So there is slowly your reverse saturation has a finite slope, right? It is not constant. It has a finite slope. That slope again depends on whether this is depends on the semiconductor material, right? For germanium, you will see that the slope is little bit higher than silicon, right? And gallium nitride, this slope will be very low, because you cannot really generate electron hole pair that easily, right? So at some point there is very high impact ionization, because your M factor will means it is infinite, right? So there your very high current flows, and that point we call the breakdown voltage, right? So if you're talking about some point somewhere here, let's say somewhere here, so the current going in the depletion region and current coming out of the depletion region, there is not much difference, right? So uh, that's the that is what the your reverse saturation current. I mean, this is, we call it reverse saturation current, but that current is not, if you go to the lab and measure, that current is not exactly constant, right? So there is a small slope, right? So but we still call it reverse saturation current. That's fine. Is it clear, Sarda?
Uh, yes, sir. So basically, my question was like here we take breakdown when m tends to infinity, but in practical scenario, like what can be the value for it for breakdown? Like in case of models, when we see, so we cannot take infinite, right? So
No, no, no. Yeah, breakdown M is called infinite, right? Because current is very high, right? Basically, if when you talk about models, um, um, okay, so I'll just so basically, if you see the so model is something like this, right? So M is if you look at a normal model, so it is model like that, right? Breakdown voltage to the power m, and m equal to 3 to 6 for silicon, right? At room temperature, room temperature, right? So so here you see this is how the m is modeled in the most of the cases. So your m is you see when your v up equal to vbr, that means m will become infinite, right? Right. So before that you have a slope, right? Finite. Your m is increasing, right? So when vf is very less, right, your m equal to 1, right? If you go on increasing applied voltage, because your vbr is constant, right? You go on increasing the applied voltage, you'll say that your m will increase, right? And at some point it will become infinite, right? So and your current that is coming out is m times I0, right? So that's the reason I was talking when you go to the reverse bias. So there is a slight slope, and at some point it will, at that point your m becomes infinite here, right, right, and this m factor here, so that depends on the material, right, because the slope, this will means this will determine the slope, and that depends on the band gap and other factors, means it's a metal properties, right.
Okay, sir. And sir, another question. So, like basically here we considered P and N plus junction. So
Hmm.
we like discarded the possibility of having whole current. Now, suppose I have normal PN. At that time, I will have both the
You will have
current.
both. You will have both electron and hole current, right? So
Yes, sir.
your so normal PN junction, you will see that at the breakdown voltage, your electron current will also be very high, and your hole current will also be very high, right? Right. So your total current
Yes.
is nothing. Means you also did, right. Your total current is nothing but a hole current plus electron current, right? So your uh, your J equal to Jn plus Jp, right. So and this is the electron current, and electron will also go, I mean electron means will also, because if you see here, you see here, I means the impact transition process is started with the electron, right. But in case of PN junction, normal PN junction, the impact transition process will be started of electron and hole both, right, because if you look at the n side, so there are some significant amount of holes will also be injected. So your impact transition process will be because of electron as well as holes, right? So electron will create impact transition as well as holes will also create impact transition, right? So your total current is your because of electron and hole, right? J equal to Jn plus J.
Yes, sir. So, sir, like in
Yeah,
that
just
case,
hold on. I have some phone call I have to attend. Okay, so Sarda, sorry.
yes, yes. So what I was saying was, is it the assumption that when electrons or holes are traveling at very high speed, they will not recombine and just like they will uh, proceed to avalanche multiplication, or like will there be any, because there are a huge number of electrons and
But
holes.
see, there is very less possibility of recombination because they're moving at very high speed, right?
Yes.
Right.
So
So
it is.
that's what we assume, that recombination is much less than generation. Okay, there will be some recombination, but that recombination will be less than generation, right? So
Okay.
yeah. So
Yes,
so
sir.
basically here the generation will be much more higher than recombination. But when if you go when you're talking about the lower reverse bias case, right? So in this at this point, right? At this point here, right? When we're talking about lower reverse bias case, there the generation is not very high, right? And there is a finite recombination also in the depletion region, right? but but you imagine, so because this is reverse bias, you have very less number of electron holes are injected to the depletion region, right? Because the current flowing through the depletion region is also very low at this condition, right? When you are in the reverse bias condition, right?
Right.
So your recombination anyway is less, and on top of that your generation is mostly less. So you and at this point your current is mostly the reverse saturation current, right? So your n is injected from p to n side, and sorry, not injected, so they're going through the drift, right? So n to p and p to n, right? But as you go on increasing your applied reverse bias, right? As you go on increasing your reverse bias, so then your things will change, because you'll have more generation, right? So and recombination will be can be neglected.
Yes, sir.
Sir, like in forward case, when we apply forward bias, so when electron goes from n side to p side, so Fermi level splits. But in this case, when
No
we are
electron, yeah, okay, huh?
in forward condition, when we apply, so electron goes from n side to p side, so Fermi level splits.
Mhm.
So in this case, when we are applying reverse bias, so when electron, we are considering the case that electron is going from n side to p side. So in this case also the Fermi Fp will split.
The electrons don't go from n to p side. Your holes go from n to p side, right? The
Yes.
reverse bias, as I told you, right? So this is a minority carrier that travels, right?
Yes.
Right, because there cannot be any injection, right? So because my barrier has increased, so there will not be any injection. So the
Okay.
minority carriers, that minority carriers holes in the n side, they will
Okay.
go through drift from n to p, and the electrons in the p side will go to n, right?
Yes.
Yeah, there
Okay.
will be some current, but there, because the current is flowing, there will be splitting, and this EFN, EFP, and EFN, right? Anyway, that is the means because I'm applying a applied reverse bias, right? So the difference between EFP and EFN will always be applied voltage times Q, right?
Oh, okay, sir.
Yeah, but please keep in mind, since the barrier height has increased, so there is no injection from N to P, right? Electrons cannot be injected from N to P, but the holes in the N side, they can go to the P side through the drift, right? So here the means here all this means current is because of drift. In the reverse bias condition, the current is because of drift, unlike diffusion that were discussed in the forward bias condition.
Okay, okay, sir.
Yeah. So see, okay. So again, all right. So basically, when you're talking about a normal PN junction, the impact transition is caused by both electrons and holes. So the total current will be Jn plus Jp, and yeah, and for n plus, for n plus p junction, it is one of the carrier, right? So p plus n junction, p plus n junction, it is caused by holes, right? And n plus p junction, the impact transition will be caused by electrons, right? So I am telling this p plus n or n plus p junctions more and more, because actually in actual devices we have very less occurrence of pn junctions, right? Either you have p plus n or n plus p junctions, right? Okay, so so this is avalanche multiplication, and in this process the breakdown is happening because of avalanche multiplication, and that will only happen when the field across your junction becomes more than the critical electric field. And the critical electric field is a metal properties, and it depends on band gap mostly, right? Higher the band gap, higher the critical electric field. So you need more voltage for junction to break down. That's the reason gallium nitride could handle more voltages across its junction compared to germanium or silicon, right? Okay, and this is avalanche multiplication, and please keep in mind avalanche multiplication is dependent on temperature. So what will happen if you increase the temperature? So will the breakdown voltage decrease or increase? Monica? Monica, are you there?
Yes, sir.
So what will happen to the breakdown voltage if I increase the temperature?
Sir, breakdown.
Hmm?
Sir, it should increase because the electron energy would increase.
So electron energy would increase means they will create more impact radiation. Hmm?
Sir, they'll have an increase in their energy. So, yes, sir.
What will happen?
Sir, I think it should increase.
What will increase? Your breakdown, see, if electrons have more energy, then they'll create more impact radiation. That means the breakdown voltage will be less, right?
Sir, there would be more impact of ionization, no?
Yeah, if there is more impact radiation, then the breakdown voltage will be less, right?
Yes, sir.
So you are telling that if you increase the temperature, your breakdown voltage will reduce.
Yes, sir, it should.
No, but see, keep in mind, anybody else, Nishant?
Sir, it will reduce.
Why should it reduce? See, okay. So how does, see, basically I told you, right? So because the electrons have very high energy, they transfer energy to the lattice for the electron hole pair generation, right? So what will happen if you increase the temperature? The lattice is vibrating, right? Lattice is vibrating means they're creating phonons, right? So the phonons, once they are creating phonons and electrons are traveling with very high speed, if electrons interact with phonon, what will happen? Their energy will reduce or increase?
Will
Reduce.
reduce.
Yeah, that will reduce, right? So basically, at high temperature, even let's say electron is increasing at very high, I mean, sorry, the electron is traveling with 4 electron volt of energy, right? But let's say, but since there is lattice scattering at high temperature, so there are phonons generated, and phonons will also interact with these traveling electrons, and the phonons will decelerate the electrons, right? So that means the electron is traveling 4 electron volt, but with the interaction with the phonons, so their energy will reduce, right? The moment their energy reduces, they have very less energy to transfer to the lattice, right? So the impact ionization process uh, will slow down, right? So as you go on increasing the temperature, the impact ionization process will slow down. That means your breakdown voltage will decrease. Breakdown voltage will increase, right? So your breakdown voltage. So please keep in mind for avalanche multiplication process. If the breakdown is because of avalanche multiplication, your breakdown voltage will increase with temperature for avalanche breakdown process, right? Right. So your VBR, your breakdown voltage will increase with temperature. This is a very means you have to remember because uh, because when the PN junction is operating at high temperature, its breakdown voltage actually increases if it is the breakdown happening because of avalanche multiplication, right? Okay, so this is about avalanche breakdown process. So there is another you could also see here. So okay, so here you see okay, this is the band diagram in the reverse bias. So if you look at here, so this is the conduction band of electrons, right? So this is the conduction band. So this side I have uh, conduction band inside, right? So so if you look at the conduction band, so you're basically when I talk about conduction band is mostly empty and valence band is filled, right? So I have let's say I have states here, right? I have states here, and most of the electrons are at the bottom of the conduction band. So let's say this much electron is conduction band is filled, but this much is empty. Similarly, if I talk about the valence band is mostly filled with electrons, because valence band uh, because so if I have holes, so some right. So let's say at the edge of the valence band there are some states which is we do not have electrons, but otherwise the valence band is filled with electron, right? But if you see this condition here, so I have a point, let's say this region here, this region here. So you see, if you look at the p side, I have filled states. If you look at the n side, I have empty states, right? So when I have filled states on the one side and empty states on the other side, the electron could tunnel, right? Right. So electrons could tunnel, and this is the classic. This is quantum mechanical tunneling process, right? So for the tunneling to happen, what are the condition? The condition is this barrier, the barrier that I'm talking about, right? Thickness of the barrier, right? Right. So you imagine, so if I have a quantum mechanical barrier here, right, and I have electron in this side, so this quantum mechanically this electron could tunnel, right, to the other side, right? And the probability of tunneling, right, tunneling probability is a function of the width of the barrier, let's say width of the barrier and height of the barrier, right? Right, let's say this height of the barrier, right? So so this part we know from the quantum mechanics, right? So the means electrons being wave like nature, so they could tunnel from one side to other side, and that tunneling probability of tunneling depends on the thickness of the barrier as well as height of the barrier, right? But also for the electrons to tunnel from one side to other side, there should be an empty states where the electron could tunnel, right? So in case of reverse bias, so if you look at the band diagram, so there is a possibility, means if you look at the p side, so there are filled states, and if you look at the n side, there are empty states. So the electrons could tunnel from the p side to the n side, and that is only possible if the depletion width is very low, right? So this depletion width should be around 100 nanometer. Uh, so this depletion width, um, so the tunneling is mostly happen if the depletion width in the order of 10 to 100 nanometer. Let me write down, not 100 nanometer. So in the order of 10 to 100 nanometer. See here, when I'm talking about tunneling, so the electrons are tunneling from p to n side, right? So electrons are tunneling from p to n side, and similarly the holes could also tunnel from n to p side, right? So holes could also tunnel from p to n side, right? um, so this is also means reverse, right? Reverse process, right? Because in the normal case in the forward bias, what is happening? Electrons are going from n to p and holes are going from p to n. But this is the reverse bias case, electrons are going from p to n and holes are going from n to p, right? But they are going from n to p not by avalanche multiplication in the earlier discussed case, but here they are going through the tunneling process, and the quantum mechanical tunneling process, and that is only possible when your this depletion width, the depletion region, right? This is the depletion region in the order of 10 to 100 nanometer, right? So this process, this tunneling, this is called this is first discovered by Nihar, so we call this Nihar tunneling. So so this process only happens because you need very small barrier thickness, and so that only happens when both the sides are heavily doped, right? So it also happens in n plus p junctions. If you would calculate the barrier width, right, n plus p junction, anyway this is n plus, this is very high doping n plus region, but the p region, if it is more than 10 to 18, right? So if you calculate the barrier width, it is order of it will be in the 10 to 100 nanometer regime, right? So for n plus p junction, if the p side is more than 10 to 18, doped more than 10 to 18, then there is a possibility of Nihar tunneling, right? So the reverse breakdown, I mean, because if you see here, this reverse saturation current is because of tunneling, right? Because your electrons are going from P to N because of tunneling, and holes are coming from N to P because of tunneling, right? And as you go on increasing the reverse bias, that means you are pulling this down, right? When you're pulling this down, when you're increasing the reverse bias, that means you are exposing more empty states to the P side, right? So this tunneling current will also increase, right? And this tunneling current has exponential depend on the on the on the applied voltage, right? So at some point, so there will be very high current flow, and that will call the breakdown, right? And that breakdown is happening because of very high current flow. Lot of states are exposed, so that electrons could easily tunnel from P side to N side. And if the barrier is very low, that current will be very high, right? And uh, so your junction will break, but the junction is breaking not because of avalanche multiplication, but because of tunneling. And this breakdown we call the Zener breakdown, because Zener has observed this phenomenon first, so he named it Zener breakdown, but this is tunneling. So breakdown is happening because of tunneling, right? So, but the condition for tunneling is you should have very high dope, right? So because tunneling will only happen if the barrier width is very low, and that is only possible if you have N plus P junction, and the P side is also a little bit highly doped, heavily doped, right? So Zener, because you see, for Zener breakdown, um, right? So we have two kind of avalanche and Zener. So if you see, Zener breakdown is observed in highly doped junctions. So the breakdown voltage is low, right? So if you see a diode has lower breakdown voltage, that means your both the sides are heavily doped, and there the breakdown phenomena is mostly by the Zener tunneling process. But if the both sides are not heavily doped, so Zener there is a very low possibility of Zener breakdown. So mostly the um, um, low breakdown case, mostly for the low breakdown voltage. So and for high breakdown voltage, so mostly the high breakdown voltage cases are avalanche breakdown process, right? Um, if both the sides are not heavily doped, right? So your barrier width is very high. If the barrier width is very high, so tunneling anyway tunneling process, the probability of tunneling will be very low. So so Zener breakdown will not happen, but your breakdown will happen by the avalanche process, right? Okay. So but also basically what has been observed, if your breakdown voltage is more than 6 to 7 volt. So this is mostly avalanche breakdown, normally avalanche breakdown, right? Avalanche breakdown. If your breakdown voltage is somewhere less than 4 volt, there because of Zener breakdown, right? In a typical PN junction, right? But somewhere between, right, we have avalanche plus Zener, right? It's very difficult to know whether this is avalanche or Zener, right? Right. So in this condition here, so if you want to see whether this is avalanche breakdown process or Zener breakdown process, so what you have to do is you have to take this PN junction, then find the breakdown voltage or measure the breakdown voltage at different temperature, right? For avalanche multiplication, we have discussed your breakdown voltage will increases with temperature, but for Zener breakdown process, your breakdown voltage reduces with temperature, decreases with temperature, because this is a tunneling, and tunneling phenomena will increase with temperature. As you go on increasing the temperature, your tunneling will be higher, because see, at high temperature the electron will have higher energy, so electron have higher kinetic energy, so tunneling will be easier, but tunneling depends on the barrier width also, right? So as you reduce the barrier width for the electron, your tunneling will be more, means tunneling probability will be more. So so avalanche breakdown has a negative temperature coefficient. So higher the, so you could see okay. So for avalanche breakdown, so your breakdown voltage If you increase temperature, your breakdown voltage will increase. This is for avalanche process, right? And for tunneling, I mean the tunneling process, your this is for tunneling process, right? So by doing the temperature dependent study, so you could find whether your breakdown is happening because of avalanche or tunneling, right? Right. So I think I should stop here because so we are already 6 minutes past um, 6 minutes past 12. So if you have any questions